Okay, so basically here we have a gas that's sitting inside the container, and the gas has two jobs. The gas has the job of pushing up on the block that's pushing down with its weight. It also has the job of pushing up on the atmospheric pressure that's pushing down. So here we have P of the atmosphere, and here we have P of the block. And it's the job of the gas to be able to actually push up on both of them. So now it's our job to find the combination of the pressure of the block and the pressure of the atmosphere. The pressure of the block just means the weight of the block over the area of the surface. The pressure of the atmosphere is given to you in the reference sheet as 1.0 times 10 to the power of 5. Now the weight of the block is 2000, and the area of the surface is 0.004 plus the pressure of the atmosphere. And the whole thing is going to come out to choice D. Okay. Question 2. This is the application of Kirchhoff's rule. Whenever you see something called a junction, that means that the current has to be entering into this node or junction and has to then spread out into two different currents. Or possibly, so look, it can maybe, in this case, spread into current A and current 1 and current 2. That's one possibility. Or the other possibility is you have a current 1 coming in and adding up to the 0.30. So now you're going to have current 1 plus 0.30 as a combination is equal to current 2. So we have two possibilities. Either it diverges or it combines with something else. Now assume that it diverged. The ones that have diverged from it must add up to it. But here they add up to a 0.60. So it's not choice A. In this case here, it seems to be combining with the 0.25. So if it combines with the 0.25, that becomes a 0.55. So it's true. B is true. Okay. Question 3. Here we have, what do we have in here? Do we have parallel or series or a combination?
A combination.
Which one is the series one?
The 2R.
Exactly. Whenever you have a parallel and a series type of resistance, you should always find the parallel branch first. And that would be this R and this R. So we're going to say 1 over R parallel, 1 over R plus 1 over R. So combine them, you get 2 over R. We must now flip it. So R parallel is simply going to be R over 2. And now you're going to have to add that with a series. So you're going to say R of the circuit is equal to 2R plus R over 2, which is 5R over 2. Now, if we're looking for the power, we have multiple rules to find the power. One of them is going to be V squared over R. And V here is just EMF. So V squared over the R of the entire circuit, because we're looking for the battery here, which would be 5R over 2. And then if you do some math, 2 EMF squared over 5R. And so the answer is going to be choice A. Question 4. If we're going to go from N of 2 to N of 4, we have to absorb a photon with a certain energy or a certain frequency. But then if we go from N4 to N1, or sorry, N1 to N4, we have to absorb a photon of more frequency, right? So to go from N1 to M4, we need to absorb a photon of more frequency because we just have to jump to a higher level. Okay, so we have to absorb the photon. And we have to absorb it with more frequency. So it's A. So look, they want the EMF induced when the loop is exiting the magnetic field. EMF is equal to B times L times V. But here we have two dimensions. We have the 1.5 meter and also the 0.7 meter. Whenever you have two dimensions, always take the dimension that happens to be perpendicular to the velocity, which means you must take the L as 0.7. And the B is the magnetic field of 0.25. And the V is the velocity, which is the 1.2. Now let's multiply all of them and see how much we get. And the answer comes out to 0.21 volt. So it's A. Look, whenever you have two plates, one of them is positively charged, one of them is negatively charged, there's going to be electric field leaving the positive plate and going to a negative plate. And this field is going to be uniform everywhere in that region. So the field here is the same as the field here, same as the field here, and same as the field here. So now, if you were to take your charge to a different placement, you will still experience the same exact field. The field has not changed. So if the field has not changed, the force has not changed either. And before, the force was just F. Now the force will still be F. Okay. 7. We have a diverging mirror. What does that tell you? Is it concave or convex? Okay. It is actually convex. So if the object is here, it looks like it's protruding out. That's what diverging mirror means. It's a convex mirror, but there is one detail we have to know here. If it's diverging mirror, the focal length has to be negative. Now here we're provided with the radius of curvature to be 20. And radius of curvature, you have to know, is 2 times F. So 20 is 2 times F. F is equal to 10. But because it should be diverging mirror, it must be a negative 10. So I'm going to say 1 over F is 1 over SO plus 1 over SI. The object distance is 25. So now 1 over 10 negative minus 1 over 25 is 1 over SI. How much would that give us?
I think I did the math wrong. I got 0.14.
Wait, flip it. So do 1 over that.
1 over 14?
1 over 0.4. Like 1 over the answer.
7.1.
Okay, so SI is equal to 7.1. The answer is going to be choice A. Very good. It's negative 7.1, right? Just to be sure. Okay, 8. So here we are going from a volume whose height is YO to a volume whose height is YO over 2. So what happened to the volume? It became less, correct? It became less. It did decrease. Okay. And if the volume decreased, so if delta V is negative, the work is positive. They're asking us right now to take care of the energy transferred by heating or cooling between the gas and surroundings. What are they asking us to find exactly?
Q.
Q. We're being asked to find the Q. So now I'm going to say delta U is equal to Q plus W. So delta U is equal to Q, and W, you should know, is negative P delta V. It's in your equation sheet. Now, has the pressure changed? No, it was P1 and still P1, so I'm going to just write negative P1. But the volume has changed. The volume in state 1 was V1, we are told, but now the volume became half V1. Would you agree? Because the volume just got halved. So now the volume change will be half V1 minus V1. So half P1 V1 is going to be our work. So plus half P1 V1. Now what's left is for us to actually find the delta U. We have now to go back to our equation sheet and bring up the equation. So I must be dealing with this equation right here. Well, if you look at the choices, we don't have the second part, just the first part. So U is equal 3 over 2 nRT. So now U is equal to 3 over 2 nRT. Right now we're dealing with delta U, right? So delta U means 3 over 2 nR T final minus T initial is equal to Q plus half P1 V1. Now, we're looking to just find the Q alone. So Q is equal to 3 over 2 nR T2 minus T1 minus half P1 V1. So the answer is going to be choice D. Okay, question 9. So look, let's just imagine what a beta is. So look, here we have, let's say x, 10, 20, beta with y. So how much should the bottom number be now in the y?
9.
Actually 11. So that the, 11 plus negative 1 gives you a 10.
Oh.
Yeah.
That's the result, okay.
Right. So now what happened to the atomic number?
Increase.
Increased.
Yeah.
But how about the mass number?
Stays the same.
Thank you. So look, how can the proton number go up by 1, but the mass number stays the same? It's because neutron number had to go down by 1 as well. Because ultimately mass number is equal to proton number plus neutron number combined. Okay? So they both have changed. Okay. Question 10. So the distance between the bands is given by the equation m lambda L over D. So with D being the distance between the slit, now we're changing the frequency. We're doubling the frequency, but there's no frequency in the equation. But that's okay, because V is equal to lambda F, or C is equal to lambda F for light. So if the F goes up by a factor of 2, lambda goes down by a factor of 2 to keep the C constant. So now imagine if the lambda went down by a factor of 2. The Y will go down by a factor of 2. Yeah? So the answer is going to be B. We'll get halved. 11. A sample of an ideal monatomic gas is sealed in a container of fixed volume. The temperature of the gas decreases. A student claims that the speed of every gas atom decreases, which obviously is wrong, right? You can't have every single atom decreasing. Mostly will decrease, but you cannot control all. So it's going to be incorrect. So look, if you bring the temperature down, the Ke will go down. So it's this. Okay, question 12. We should now bring up the equation that the resistance of a resistor depends on. So R is equal to phi length over the area, the cross-sectional area, which is the area of a circle, right? Which is pi r squared. But here provided with d. So R is equal to d over 2. So that means pi r squared just means pi d squared over 4. So essentially the R is going to be direct with the length, but inverse with the d squared. Now, let's just do the proportion or the ratio for resistance 1. So you're going to do L over d squared. For resistance 2, L over 4d squared. Would you agree we're just squaring the d? For 3, it's going to be 2L over 4d squared. And that would be L over 2d squared. So which one of these is the biggest number? Like, ignore the L, ignore the d squared. This would be a 1. This would be a fourth. And this would be a half. So the biggest number here is resistor 1. Then 3.
Then 2.
Then 2. Okay. Question 13 here. So here we have three figures. We have two figures, but we have three insulating stands with three spheres. So initially, sphere X is positively charged. Okay. And spheres Y and Z are not charged. Now look, if you are bringing a positively charged sphere, which is the X, next to those two spheres which are attached to each other, all the negatives will go here, and all the positives will go on Z. Exactly. And now if you have all the negatives here and all the positives here, so now Z became positive and Y became negative. So the answer is going to be D. Okay. Question 14. Do you know what this constant means or this symbol means?
Torque?
That's torque, but not in this case. It's a different symbol here. This is called the time constant. It's new. It's actually this year came out. And the time constant is going to be the R total times
the new book? The new Princeton version?
Of course not.
Yeah, that's why I don't know.
Book sucks.
A lot. It's useless.
Semi-useless, yeah. It's like going to the gym. When you go to the gym, you have to stretch, right? The stretching is the Princeton review. And the weights are the exams and the College Board's files. So what you want to do is, here it says, the circuit initialized time constant of this. So we're going to say that I'll call it T for now. It's not T, it has a different name, this symbol.
Is it on the equation sheet?
No, but we don't need to know. It has a name, the symbol has a name.
Constant.
No, like this symbol.
With
this weird T has a name.
Okay.
In Greek, but we don't care about that, do we? RO times the capacitance, which is just a CO. Now, what happens is they change the resistance and they change the capacitance and they say, will we still get a TO like before? So let's see what that means. C is going to be inverse with distance between the capacitor plates, correct? So let's look at this scenario. Here we are going to be halving the R. And if you were to basically increase the distance between the capacitor plates by the root of 2, that means you will decrease the capacitance by the root of 2. Decrease it. So that means you will simply replace C with C over the root of 2. Will that give you RC? That will give you RC over 2 root 2, right? So it's not going to be that one. Okay, now C is going to be inverse with distance. That means if you double the distance, like they did in part B, you will have the capacitance. This will be RO over 2 times CO over 2. You get ROCO over 4. So you're not going to get ROCO. No. No. So 2RO, and if you were to double the distance, you must have the capacitance. So you're going to get CO over 2. You get ROCO. So it is choice C. 15. Here we have an electron entering into a magnetic field area, and it's entering in a perpendicular fashion. So that means you have to undergo a circular motion under the influence of magnetic force. But we're dealing with an electron, we have to use the left-hand rule. Anyways, there's no need to because they're all going to be going to the right side. But again, you have to undergo a circular motion. So it's not A.
It's not B.
It's not B. Either C or D. You only undergo the circular motion when you're inside the field.
Yeah.
Once you have left the field, you just have to go in a straight way compared to where you are. So for example, here, you are leaving the field at this point. That means you just have to continue forward.
Yeah, it shouldn't curve.
It shouldn't curve anymore because there's no more influence of the field. So it's not D.
Let's see.
It is choice C. Okay. Question 16. So, can we find the Q or the heat?
I think, yeah.
Okay. So do you know what power means? Power means energy or heat over time. So energy or heat is equal to power times time. Okay, but we don't know what the energy is. So energy here is just Q is equal to mc delta T. M is the mass, C is the specific heat capacity, 4,200. Delta T is the change in temperature, which is 10 Celsius. Actually, there is one thing that I missed here. This is in grams, that is in kilograms. I must divide my mass by 1,000. So let's go ahead and see how much we get. One to 600 joules. So here the heat will be 1 to 600 is equal to the power times the time. So the time is equal to this number divided by this number.
25.2.
So choice B. 17. You want to find the work? Fine. But you must do it for 3 different times. How so? I will call this Q1, Q2, Q3. You must find the work for Q1, Q2. You must find the work for Q1, Q3. You must find the work for Q2, Q3. You must then add them all up. And work is without any absolute value. So if the product of the Q's is negative, you must get a negative work. Now, what's the equation for work? K, Q times the other Q over R. So all the works here have K in them, right? They all have K. So I'm just going to say the work is equal. I'll put the K outside. So I'll do Q1 times Q2 over R. Q1 times Q3 over R. Then Q2 times Q3 over R. Now simply replace the K with how much?
9 point something.
Yep.
9 point.
Yeah,
Yeah.
got you. -3 times that. You have to be very careful to plug it in here because it's lots of numbers.
I usually just do it all in the calculator. I'm scared of running out of time.
What do you mean? What?
In the exam, I would just do it in the calculator to not run out of time.
Yeah, I am doing a calculator.
I mean, without writing it down.
Oh, without? Oh. That's hard. If I'm lucky. Oh, stop typing. No. It stopped typing for me. Oh, God. Okay, I will do it in 2 steps. So basically, I will do it in 2 steps. So right now I did it for this times this plus that. I got this much. Now I'll do it for the last one. So now I'll do decay times that. I got minus. Okay, I got A. Good. Question 18. So we know that voltmeters should have a very high resistance that no current even dares to go through them. But that's normal voltmeters. If we have non-ideal voltmeters, the rules will be tweaked a bit. Okay, meaning what? They will themselves act as a resistance. That's what it means. So imagine here if you have a resistance. Now you have 2 resistors in parallel, which will bring the R of the circuit down. So now the current in the circuit is no longer applicable to a single R. Now it's applicable to less than before because now the R actually went down. So this equation is no longer correct. When is this equation correct? If your voltmeter was ideal, which means nothing goes through it, or if you just had this configuration, your equation would be right. But now by having non-ideal voltmeter, your R of the circuit will go down, so this equation is no longer going to be applicable. So it's not a yes. Okay. And no, the potential difference across the resistor is not going to change. It's not, because it's in parallel with the thingy. But what's going to happen now is that the voltmeter is going to act as a resistance of its own, and it's going to change the resistance of the entire circuit. So it's choice D. Question 19. So Okay, now here we actually have talked about something very important, which is that a pipe that's open at one end and closed at the other end must have this equation. L is equal 1 over 4 lambda L, lambda N. But this equation is not provided to you in the equation sheet. So you gotta be very careful. Now, we're talking about the fundamental harmonic. That means that N is equal to 1. So L is equal to 1 over 4 lambda. So right now our job is just to find the lambda. And V is equal to lambda F for a sound wave. So a 340 is equal to lambda times 260. Lambda is equal 340 over 260. And I got 1.30 as the lambda. So now L is equal 1 over 4 times 1.30. And I got a 20. So Y, which is the separation, so the distance between those peaks is called a Y. It's m lambda L over D. L being the distance from the screen to the slits. So now if the L goes up and Y is direct with it, Y should also go down. So now the peaks have to be spread out away from each other.
Like C.
Which only happens in choice C. 21. So if you look back at question 20, we were using light of a wavelength of lambda. But now imagine if you replace that with two lights instead. One is 3 over 4 lambda, one is 4 over 3 lambda. So now what's going to happen to the interference pattern? Will it be the same as before or not? Of course it's going to be different because you went from a single light to now two lights. So of course you're going to have a different pattern, and those wavelengths are different from each other. Not the same wavelength. And different wavelengths means different light interference, because ultimately Y is equal to lambda L, m lambda L over D. And so the lambda being different means different Y, means different interference pattern. And so it's going to be C. They're going to have different distance between the maxima because we have different Y. 22. Do we have here parallel or series or both? Which one is the series one?
The 15.
Thank you. So we'll start by finding the R parallel. So 1 over 30 plus 1 over 30 is equal to over 30. You must then do what? Flip, and you get 15.
And then you add them.
Yep, so now the R of the circuit is equal to 15 that we just got, plus 15 that's in series, and the whole thing is 30. Okay, 23. We're talking about the force that one particle exerts on the other. So what's the expression for the force, electrostatic force? K, Q1, Q2 over R squared, and they are 4D squared. You see how I ignored the minus sign of the negative 2Q? Because the equation for the force has an absolute value in it. And now we just do some math. So we're going to get 8Q squared over 16D squared. So K, q squared over d squared times half, which is choice B. Question 24. So look, from A to B, what's happening to our pressure?
Increase. No.
It's actually not changing,
Not
right?
changing,
But the
yeah.
volume has changed.
Yeah.
So from A to B, the pressure is constant, the volume increased. And as we know, if the pressure is constant and the volume increases, temperature has to also increase. So now we know that temperature of B is more than temperature of A. Okay, so C and D are out. How about from B to C? Is the pressure changing?
Yes.
Yes. Is it increasing or decreasing?
Increasing.
And how about the...
The volume is constant.
Thank you. So now, if the volume is constant and P decreases, T also has to decrease. So it's going to be increase followed by a decrease, which is choice B.
Yeah.
25. Let's imagine this circuit. So here we have a battery, long line, and a short line with internal resistance, which means you must always draw it in series, is connected in series with two other resistors. Okay. If we were to apply Kirchhoff's rule, it says whatever goes out has to come back in. And so if we minus them, we get a 0. Okay. So I'm going to say EMF. Whatever comes after EMF has to be a minus. So minus what? I times small r minus I times capital R minus I times capital R. The whole thing must be equal to what?
0.
To 0. Okay. Now let's just combine the I capital R's. We'll get 2IR is equal 0. How about now we move anything with the I to the other side? And now simply I can factor the I out. So now I is equal to EMF R plus 2R. Okay. Now that's an important step. What the question wants is the potential difference across the battery. And you must know that the potential difference across the battery is simply the EMF minus the voltage wasted in the internal resistance. So now, this will be the EMF minus the voltage wasted in the internal resistance. So EMF minus, instead of I, put EMF R plus 2R times small r. And it seems that here they factored the EMF out. I'll do the same thing. So EMF 1 minus small r, r plus 2r. And the answer is choice C. '26. So here the N2 is bigger than the N1. So will the light refract toward or away from? Refract toward. That means that your theta R will be less than your theta I. But it is a rule that you have to know because of Snell's law that as you increase the angle of the incidence, the angle of the refraction will also increase. Okay. Now, let's just talk about Snell's law for a second. So we're going to say sine theta I times n1 is equal sine theta r times n2. And here, if you look at the figures, we are plotting sine theta r as the y-axis and sine theta I as the x-axis. So I will just say that sine theta r over sine theta I is equal to n1 over the n2. So now it's like saying y over x is equal to the slope. So the slope is equal to n1 over the n2. And since the n2 is more than the n1, then n1 over n2 has to be less than 0. Your slope, sorry, not less than 0. Less than 1. Less than 1. And so your slope has to be less than 1, but it's a positive slope, right? Because both numbers are positives. So it's more than 0, but less than 1. So it is not B. It is not A. It has to be more than 0. And we also know that when there's more theta I, there's more theta R. That means you must have a slope that's going up, not going down. But it's less than 1, the slope. So which slope here is less than 1? C or D? Exactly. Okay. If someone's confused about why the slope in D is less than, is not the answer, we can find the slope. So we can say 0, 0 with, let's say, that. Which will be 0. Let's say 4 with 0.75. So y2 minus y1, you will get more than 1 as the slope, which is not okay. Let's find the slope in C. So 0, 0 with, let's say, 0.75 and let's say 0.85 or something like that. So we're going to say 0.85 as the x and 0.75 as the y. This is 0, 0, so y2 minus y1, x2 minus x1. That would be less than 1, but bigger than 0. So it's perfectly choice C. Question 27. Okay, we have talked about something called the conservation of momentum here. Momentum is conserved unless there is an outward force. But there is nothing mentioned here about outward force. That means the momentum before is equal to momentum after. So, momentum before is equal to momentum after. Momentum before is equal to momentum after. So which one is that? B, because if you just move, that PF to the other side becomes negative. 28. So the magnetic force is causing a centripetal force. So essentially QVB is equal to mv squared over r. Cancel a square with a v. So QB is equal to mv over r. R is equal to mv over QB. So it's choice E. Someone's going to say, what is this E? E just means the Q. It's in your equation sheet. It's called elementary charge. Okay. Question 29. As we go from A to B, what are we experiencing? Are we experiencing a change in volume? No. The volume is constant. So that means that delta V is 0. That means the work will also be 0. Now, as we know from the first law of thermodynamics, delta U is equal to Q plus W. So W is 0. So delta U is simply equal to Q. So the sign of Q depends on the sign of delta U. And as we go from A to B, the pressure in B is more than the pressure of A. That means temperature of B is more than temperature in A. And so delta U is positive because temperature increases. So Q must also be positive. So we're heating the system basically. 30. Okay, so we've seen this figure before, but with a different y-axis. I mean x-axis. Before, the x-axis was F, but now it's momentum. P means momentum. Things have changed here a bit. We have talked about de Broglie wavelength then, because ultimately, lambda is equal to h over p. That's the equation. Now, c is equal to lambda f, so lambda is equal to c over f. So here, replace lambda with c over f. Okay, now the work function is equal to h times the threshold frequency. So here, the frequency expression is equal to c times momentum over the h. And if we're looking at the threshold frequency, we must be talking about the first point when the electron starts to leave, which happens at 2po. So come here and replace the f of o with c times 2po over h. So do we see our answer in there? We do if we cancel the h's, right? So c 2po. (31) An air-filled parallel plate capacitor has a capacitance of CO. And we're going to put a dielectric constant. Now you have to know that C is direct with dielectric constant. And so if it's 2, that means the C goes up by a factor of 2. Yeah. So it's D very easily. 32. So here, what's happening is that we have a positively charged particle. That means you must be applying the right-hand rule. And it's going to be entering an electric field that's going to be pointing upward and a magnetic field that's pointing out of the page. Right-hand rule for the magnetic field. So point your thumb left. Point the fingertips out of the page. And your palm will be heading upward. So that means that the influence of the magnetic force should be to push the particle upward. Now, electric field always is heading from the positive plate toward the negative plate. Sorry, I meant that the thumb has to point down. Yeah. So magnetic
Wait,
force. Yeah. Right hand rule. Right hand rule.
Right.
So the charge is pointing right, the field out of the page, the force pointing down.
Oh.
Yeah. But the electric force is pushing it upward. But somehow it keeps moving in a in a straight line. Meaning that the magnetic force is equal to the electric force. Okay, so QVB is equal to QE. Q's cancel, so the electric field is equal to the V times the B. In the second scenario, the magnitude of the magnetic field is 2B, but the same V. So now the B doubled. What happens to the E? Exactly. $33. So look, a beam of light in a transparent medium with index of refraction n is incident on the boundary with another transparent medium with a greater index of refraction n2. The incident beam makes an angle of theta I with the normal. If theta I is varied, what's going to happen? Can we get TIR? Look, for you to get TIR, you have to go from more n to less n. That's how you get TIR. But here we're going to be basically going from less n to more n. So there's no way to get TIR. So it's not a yes.
It's D.
It's D. Because if you go from less n to more n, you actually will refract toward, which is true. 34. The longer the line, the more the energy, and therefore the more the frequency. So line X has the most energy, the most frequency. And with the most frequency comes the least wavelengths. Okay. So X has to be the least wavelength, not the most. So it's not A. And it is not
B either.
C. Right, so Y and Z have different lengths. They must have different wavelengths. Good. 35. So okay, let's take a look at this question. So let's find the average electric field between x of 0.10 and x of 0.20. Now look, let's just think about it this way. If we're looking at the average electric field, we have to be using the following equation. E average is equal to the change in the potential over the change in the distance. Okay. Now, we know that we're dealing with x of 0.10 and x of 0.20. So right now, if you minus them, you will get 0.10. That's easy. But how about the voltages? Well, by the way, this has an absolute value to it. How about the voltages? We must find the voltage at x of 0.10 and the voltage x of 0.20. you're going to have to simply subtract them. So let's find the voltage at 0.10 for a start. So I'm going to say K, Q, over the distance. How far is this charge from the 0.10?
Which one from which?
How far is the charge that's highlighted in yellow from the 0.10?
0.05?
Yes. 0.05 plus K, and this how far is the charge highlighted in orange from the 0.10?
0.15.
0.15. Now you know what K is, right?
Yeah.
Okay, so let's use the calculator and replace and try to get the answer. I got 570 volts. Now, we'll do the work again, but now for the other point, which is the 0.20. So, let me just write the 570 volts somewhere else. Okay, now at the 0.20, how far is the charge highlighted in orange from that?
0.20. 0.15.
Yes. And how far is the charge in orange from that?
0.05.
Good. Now replace the K and let's find the answer. And I got 750 volts. Now, of course, delta V means you have to minus the V's. 750 minus 570 over 0.10, and you get the answer. How much would you get?
$1,800.
Right. So choice D is the answer. $36. Okay. Here we have a converging lens. So it's going to be thick in the middle. And we have multiple distances. So when the object is at 5 centimeters, the image is virtual. When it is at 10 centimeters, the image is still virtual. But then, once we move further,
It becomes real.
the image becomes real. So now if I move a bit further, where now it's 15 centimeters and 25, now all of a sudden the image becomes real. So there's going to be a switch for the image identity from 10 to 15. Now don't forget, for a converging lens, if the object is sitting within the focal length, it is going to be virtual. But if it's sitting outside the focal length, it's going to be real. So here the focal length happens to be between who and who? Between the 15 centimeters and the 10 centimeters. So it's choice C. $37. Okay, here we have a current with, a wire with a current that is causing a magnetic field at point P. We're trying to find what the magnetic field is. Using this equation, B is equal to mu I over 2 pi r. So the mu is actually given to you in your equation sheet. Do you know what that is?
It's in the equation sheet, so
I believe it's 4 pi times 10 to the power of negative 7.
yes.
And the I is the current 1.5, 2 pi r, which is distance from the point. So of course you can ignore the pi's, and you're going to do the math without the pi's, and let's see how much we get. (1.5 times 10 to the power of negative 6 Tesla). So it's going to be either A or B. The question is, what exactly is the direction? For the current, you have to use your right-hand rule. So, point your thumb to the right side. And you have to curl under the wire. The fingertips will point into the page under the wire, but they will point out of the page above the wire. So at point P, which is out of the page, the answer is going to be choice A. $38. An object is placed in front of a converging lens, and as you can see, it's outside the focal length. That means the image has to be real, and it has to be inverted, and it has to also appear on the other side. So somewhere here. Okay. The lens is now removed and replaced with another converging lens with a smaller focal length. How would that change things? So look, 1 over F, 1 over SI, plus 1 over SO. The focal length is less, but the SO is the same, right? Object has not changed in terms of distance. Image distance will change. So look, let's see. Before, 1 over F is equal 1 over F minus 1 over SO is 1 over SI. So right now, if I, make them into the same denominator, I'm going to have F times SO, SO minus F. And now if I flip, I will have SI is equal to SO minus F, F times SO. So now the focal length has decreased, right?
I think.
Yeah, that's what they said. We have a less focal length than before. And so, shall we just put random values to make our life easier?
Sure.
Let's say here F is 20. And let's say here object is 50. So let's see how much is the SI before. So 20 times 50, 50 minus 20. That is 1000 over 30, which is, I'm assuming, is 33. Is it?
Yeah.
Okay.
33.333.
Okay. Now the new stuff. So now the focal length is less. So I'll just say that now the focal length became let's say 15. So focal length times the SO, which is still the same, SO minus 15. So let's see how much we get now. So now I got 21. So the image distance now became less. So it's not A, and it's not C. How about the magnification? Magnification is equal to SI over the SO absolute value. So if the SI went down, magnification will also go down, right? So D. Question 39. At time of 0, the two wave pulses at locations shown in the figure are moving toward each other with a speed of 1 centimeter per second on the string. The grid lines in the figure are 1 centimeter apart. Which graph best represents the string at time of 3? First of all, are they going to interfere constructively or destructively?
I don't know.
Destructive, because one is a crest, one is a trough. So they're going to reduce each other.
Yeah.
Now, so this is right now at two blocks, and this is just 1 block. So you must do 2 minus 1. You must have 1 block down. 1 block down, which means A. 1 block down. $40. So let's use Kirchhoff's rule. Here we have 3I going in, I going in, and 2I going out. So we're going to have 3I plus I minus 2I. We get 2I. Now the force on a current carrying wire that is placed within a magnetic field is given by the equation ILB. But here our I is 2I. So it's not C and it's not D. Use the right hand rule for current in a wire. Place the thumb to the left and the fingertips to the top of the page for the dots. And the palm must be pointing upward. The palm is the force pointing upward to the top of the page.